So we are about to learn what do you mean by a complete measure space, and the definition is as follow. A measure space X B mu is said to be complete if B contains all subsets of sets of measure 0. So a measure space is said to be complete if if the collection contains all subsets of sets of measure 0. That means if I have a set E to be in the collection and measure of E to be 0 and say E1 is a subset of E, then that implies E1 belongs to B. That is what do you mean by complete measure space. I have a set in the collection. If the measure of that set is 0 and if we have a subset of that set which is of measure 0, then that subset will be in the collection. So this is what measure space mean. To look at an example, I have the R, M, M. So the set of all real numbers with set of all Lebesgue measurable sets with measure to be Lebesgue measure is a complete measure space. Also recall the fact that in case of an usual measure or normal measure, if we have E to be a measurable set and if measure of E is 0 and if E1 is a subset of E, then we have E1 to be measurable. So if we have E to be a measurable set with measure 0 and if I have a subset E1 of E, then E1 is measurable. So that's what we had in the previous case. Next we have a theorem. If X B mu is a measure space, then we can find a complete measure space, say X B naught mu naught, such that B is contained in B naught. E belongs to B implies mu naught of E is same as mu of E, and E belongs to B naught if and only if E can be expressed as a union of two sets, say A and B, where A is coming from the collection B and B is a subset of a set, say C, where C is again coming from the collection B and measure of C is 0. So the thing we need to prove is if XB mu is a measure space, then there is another complete measure space, say X B naught mu naught, such that B is contained in B naught. E belongs to B implies mu naught of E same as mu of E, and E belongs to B naught if and only if E can be expressed as the union of two sets, say A and B, where the first set is coming from the collection and the second set is contained in a set, say C, where that set is coming from the collection along with the measure of set to be 0. So we have these three things. Now in order to prove that X B naught mu naught is a complete measure space, I need to prove, that if it should be a space, first of all measure space, this should be a sigma algebra and this should be a well-defined measure. So in order to prove this as a complete measure, I need to prove three things in row. For the first, I need to prove B naught is a sigma algebra, and then I need to prove mu naught is a well-defined measure, and then finally I will come at to prove that it is a complete measure space by the definition. So let me see the proof now. Coming into the proof, I will define a collection, say B naught, of the form set of all E which are subsets of X, and clearly by definition or by the statement of the theorem, we have if E to be a member in B naught, then it takes the form E to be A union B, where A is coming from the collection B and B is contained in a set, say C, along with C to be in B with the measure of C to be 0. So by statement of the theorem, if a set is in B naught, then it takes the form A union B, where the first A is coming from the collection and the second set is contained in C, and that set is in the collection with measure of that set to be 0. So clearly I can have a collection of this form. For the first, clearly B is contained in B naught. B is contained in B naught, because if I consider a set A in B, then I can express A as union with empty set. So I expressed A with union with empty set, along with empty set is contained in empty set, with empty set is in B, where B is a sigma algebra, so empty set is a member of B, empty set is a member of B, and measure of empty set is 0. So measure of empty set is 0. So having A to B in the collection, I expressed A to be of the form A union empty set, so that it satisfies all the properties to be a member of B naught. So now I have A to be in B naught. Since A was in B, this clearly implies B is contained in B naught. Now we will prove that B naught is a sigma algebra. For the first, I have empty set to be in B naught, because having empty set to be a member of B, since B is a sigma algebra, and having proved B is contained in B naught, we have empty set to be in B naught. Next, in order to prove B naught to be a sigma algebra, it is enough to prove if I consider a set in B naught, its complement is in B naught, and B naught is closed under countable union. So now if I consider a set E in B naught, then by definition of the collection, E takes the form A union B. Again, A is in collection B, and B is contained in C, where C is in B, and measure of C to be 0. So in order to prove E complement is in B naught, considering E complement, which is same as A union B whole complement, and by De Morgan's law, this is same as E complement intersection B complement. And now listen it carefully. A complement intersection, I will replace B complement by C complement union C intersection B complement. So I am replacing B complement by C complement union with C intersection B complement. So that C intersection B complement is B complement, and A intersection this complement will be same as A intersection A complement intersection B complement. And again, this is clearly same as A complement intersection C complement union A complement intersection C intersection B complement. So now I have able to express E complement as union of two sets, where clearly the set in the first set in the union is in B. Clearly this is a member of the collection, and the second set is contained in C. So A complement intersection C intersection B is contained in C. So this is clearly contained in C, with also measure of C to be 0. So having this, I am able to express E complement as union of two sets satisfying all the criteria of a set to be member of B naught. So I have E complement to be member of B naught. Now I am remaining to prove that B naught is closed under countable union. So in order to prove B naught to be closed under countable union, I will consider a sequence of sets, say EI in B naught. Considering EI to be sequence in B naught, so by the definition of B naught, I can express elements of the sequence as a union of I say A union BI, again where AI is in B, BI is contained in say CI, where CI is again in B, with measure of each CI's to be 0. So having this, if I consider countable union of EI's, it is same as countable union of AI union BI, which is same as countable union of AI union countable union of BI's. And clearly this union is contained in or belong to B, and this is contained in a union CI, along with the union of CI is in B, where measure of union of CIs are 0 since a measure of each CIs is 0. So now we proved that B naught is closed under countable union, which proves B naught is a sigma algebra. Now having proved B naught to be sigma algebra, we are remaining to define a measure mu naught and to prove that measure is well defined. So that having proved B naught to be sigma algebra and defining a measure and proving that to be a well defined measure, then we will get into to prove that x B naught mu naught is a complete measure space. So now we will define a measure mu naught and show that it is well defined. Next, I will define a measure, say mu naught, and I will prove that it is well defined, and then we will prove that it is a measure. So for the first, I will define a non-negative extended set function, a non-negative extended set function, say mu naught, it is mapping from a collection say B naught to 0 infinity. So having defined the map to be of mu naught like this, if I consider a set E in the collection B naught, then by the statement of the theorem we will be having E to be union of two sets say A and B. And again the first set will be coming from the collection and the second set will be contained in a set say C. That set will be in the collection with the measure of that set to be 0. Now having the set E to be of the form like this, I will define the mu naught, the measure to be mu naught of E to be the measure of the first set in the union. So I am defining mu naught of E to be mu of A, so that I will show that the measure what we have defined is well defined. We will prove that it is well defined by the method that if E is a union of any two sets, say other sets A1 and B1, if E is a union of any two sets, say other sets A1 and B1, then if I prove that mu of A is same as mu of A1, then that implies that mu naught is well defined. So for the first, I will consider the set A1, and clearly this is contained in A1 union B1. So A1 is contained in A1 union B1, and this is nothing but equal to E. So I have expressed A1 union B1 as E, so it is equal to E. Along with that, in the same case, we have A1 to be coming from B and B1 to be contained in say C1, and C1 will be coming from B along with the measure of C1 to be 0. So considering A1 containing A1 union B1, and as this is same as E, and again E is A union B, so I do have A1 to be contained in A union B, and since A union B is contained in A union C, as B is contained in C, we have A union to be in A union C, so this implies A1 is contained in A union C, and by monotonicity we have mu of A1 to be less than or equal to mu of A plus mu of C, and since we have a measure of C to be 0, have in particular mu of A1 to be less than or equal to mu of A. If I call this to be inequality 1, now it is remaining to prove that mu of A is less than or equal to mu of A1. In the same lines, if I consider the set A, this is again clearly contained in A union B, which is same as E, and again E is A1 union B1, and again this is contained in A1 union C1, as B1 is contained in C1, so that I do have by monotonicity A to be contained in A1 union C1, so that mu of A is less than or equal to mu of A1 plus mu of C1. So since measure of C1 is 0, we again have mu of A to be less than or equal to mu of A1. So from inequality 1 and 2, I have mu of A to be equal to mu of A1. So if I have E to be the union of another two sets, I have measure of A to be same as measure of A1. So that implies mu naught is well defined. So we have mu naught to be well defined. So now we will get in to prove that mu naught is a measure. Next, to prove mu naught is a measure, for the first I have mu naught of A to be same as mu of A for each A in B naught. So I have mu naught of A to be mu of A for each A in B naught, again because if I have A in B naught, then I can express A to be A union empty. Again, A is in B naught clearly, and empty set is contained in empty set, and measure of empty set to be 0 as mu is a measure. So for the first I have mu naught to be equal to mu of A. Now in order to prove mu naught is a measure, I need to prove it is a non-negative extended set function. Measure of mu naught of empty set is 0 and mu naught is countably additive. Clearly by the definition of mu naught, it is a mapping from B naught to 0 infinity. It is a non-negative extended set function, and also with mu naught of empty set to be same as mu of empty set, as by the definition I have, since mu is a measure, I have it to be 0. So mu naught of empty set is also 0. We are left with to prove that mu naught is countably additive. In order to consider that, I will consider a set of sequence of sets, say EI in B naught. So if EI is in B naught, then that implies EI can be expressed as union of say AI BI, again where AI will be in the collection B, BI is contained in say CI, for CI to be in B with measure of CI to be 0. So having this, I will consider the countable union of EIs. So if I consider this, it is same as countable union of AI union BI, and again this is nothing but countable union of AI union countable union of BI. And again we should note that since BI is a second set in that union, again union of BIs will be contained in union of CIs, for union of CIs to be in B, and measure of union of CIs is 0. Since we have measure of unions of CIs is 0, I have measure of union to be equal to measure of AIs. So I am left with now countable union of EIs to be same as countable union of AIs. But since mu is a measure, I do have mu of summation of EI, if you consider, and that is equal to mu of summation of AIs. Since mu is a measure, I have this, and again if I consider mu naught of union of EIs, and this is same as measure of union of AIs. And since this is nothing but since mu is a measure, this is to be countably subadditive. So I have this to be measure of summation of measures of. So this is nothing but summation of measures of AIs. So summation of measure of AIs, and since this is equal to this, I have this to be summation of mu naught of AIs. So this clearly implies, okay, sorry, this is A and this is E. So clearly this implies mu naught is countably additive, which proves that mu naught is a measure. So finally we are left to prove that X B naught mu naught to be a complete measure space. In order to prove this by the definition, recall that this is said to be a complete measure space if it contains all subsets of a sets of measure 0. So this space should contain all subsets of sets of measure 0. In the sense, if I have E to be a member of B naught along with the measure of E to be 0, then if E1 is any subset of E, we need to prove that E1 is in B naught. So this is what we mean by complete measure space. If the E is a member of collection with the measure of E to be 0 and E1 is any subset of E, then that subset is in the collection. This is what we mean by complete measure space. So if E1 is any subset with E to be in B naught, my claim is should be I need to prove E1 belongs to B0. So in order to prove that, since E is a member of B0, I can express E to be A union B, where A is coming from B and B is contained in C, along with C is in collection with measure of C to be 0. So in order to prove E1 is in B0, considering E1, I can express this as a union of E1 with empty set. So again, this is same as E1 intersection E. Since E1 is a subset of E, we have E1 intersection E to be E1. Now I will replace E by A union B. Since E is a union of two sets, I am replacing this. Again, still this is same as E1 intersection A union C, because we have C to be contained, B to be contained in C, so that it still remains A union C equal to A union C. Now I am able to express E1 as union of two sets, where the first set is in B0, clearly empty set is in B0, and second set E1 intersection A union C is clearly contained in A union C. Also A union C is a member of B0, together with measure of A union C is 0. So I am able to express E1 as union of two sets, where first set is the member of B0, clearly it is, and this is contained in A union C, and A union C is again in B0, and measure of A union C is 0. All these things are clear, except to see again measure of A union C is 0, because measure of A union C is less than or equal to measure of A plus measure of C, and by the definition we have defined measure of A to be mu naught of E. So this is equal to mu naught of E plus measure of C, and mu naught of E is 0. So, and again measure of C is 0, so we have this to be 0. So I have measure of A union C to be 0. So this is a union which satisfies all the conditions to be the member of the collection B0. So clearly E1 is in B0, which suggests us that X B0 mu naught is a complete measure space, which completes the proof. At the last we have some properties of measure mu. So see that let XB be a measurable space, and let mu1, mu2 be two measures defined on XP, and if I have mu to be mu1 and mu2, so we will see that sum of two measures is also a measure. To see that clearly, we have mu to be a non-negative extended function, as mu1 and mu2 are non-negative extended functions. Also, measure of empty set is 0, as mu1 and mu2 are measures. We have mu1 of empty and mu2 of empty set to be 0. And finally, mu is countably additive, because if I consider any sequence of disjoint sets EI, which is a member of the collection B, I have measure of union of EIs should be to be measure of U1 union EI plus U2 union EI, which is same as summation, because since mu1 and mu2 are measures, we have those are countably additive. So we have finally it is equal to summation of mu I, which proves that sum of two measures is measure. So we have sum of two measures to be measure, and also we have if we multiply a non-negative real number to the measure, we have that measure to be also a measure. So if C is any non-negative real number, I have that also to be a measure. Also, if I have mu to be a linear combination of two measures, I have that to be also a measure. So mu is expressed as a linear combination of two measures, and again if C1 and C2 are non-negative, we have mu to be a measure. But finally we have difference between any two measures, mu need not be a measure, because if I define mu to be mu1 minus mu2 along with measure of E1 to be infinity and measure of E2 second measure to be infinity, then we have mu1 minus mu2 to be infinity minus infinity, which is not defined, so that mu1 minus mu2 need not be a measure. So if we need this to be a measure, either of mu1 and mu2 to be finite. So this completes the properties of measures.